Hi, yesterday we talked about converting 3 dimensions rectangular coordinates into cylindrical coordinates. Today we're going to talk about converting into spherical coordinates. Now, where cylindrical coordinates basically dealt with anything that can be written as and drawn as a cylinder up to a certain point, right? So how a cylinder works, like if we have a circular bottom, if we were to go out a certain distance, radius, at a certain angle, theta, right there, we could, let me go and zoom in here, kind of hard to see that. We could find any point on this system by looking at the xy coordinate down here, which would be given as r cosine theta, r sine theta, and coming up here a certain z value, at a height of a z value. So we can find any point like that. Today we're going to take a look at spherical coordinates. Now, where the cylindrical coordinates dealt with shapes that can be written as a cylinder, drawn really easy for functions drawn as a cylinder, spherical coordinates, you got to guess, are really good for any function that can be written as a sphere. Now, these are a little bit more complicated than our cylindrical coordinates. So let's take a look at them. Another way we can describe three-dimensional equation is by using a spherical coordinate system. In spherical coordinates, each point is still represented by an ordered triplet. The first coordinate is the distance. Now, so if we look right here, if I have a point P right here, we'll call it, as let's say it says X, Y, and Z. We are going to, the first coordinate is the distance from the center. For example, in this case, it's going to be this Greek letter rho, which for us is basically the radius of a sphere, kind of thing like that. The second and third coordinate is similar to latitude and longitude on a globe. So we're going to talk a little bit about this today. So the first coordinate is going to be rho. That's, like I said, is our radius. But let's talk about how we get the second and third coordinate. And that's down here. In the spherical coordinate system, the point P in place is represented by the ordered triplet, rho, theta, phi, where rho is the distance between P and the origin. Basically, it's the radius, like we just said before. And rho is always greater than 0, because it's a distance. Theta is the same as we use in our cylindrical system. So theta is basically, it's the angle on the xy plane. Right there. Phi is the angle measured from the positive z-axis and the line joining the center point. So phi, so here's my positive z, and if this is my rho, phi is the angle measured between the z-axis and that line right there. So we always measure from positive z, and it's measured from positive z-axis. And if you notice, it's going to go from 0 to pi. Now, so it goes from 0 to pi, and it's very important because if z positive is 0, z negative axis is, so the z negative axis would be pi. So we go rho, theta, and phi. So if we kind of measure like this way, so if I have any point, I start with my radius, and I'm going to rotate it around the z-axis parallel to the xy plane to get theta, and then I just measure the angle from the z-axis itself. It's not that hard to do. Now, there are some conversions. If you notice, these are very nasty to do. To convert from spherical to rectangular, x is going to be rho sine phi cosine theta. Y is going to be rho sine phi sine theta. We're not going to prove these. And z is just going to be rho cosine theta. That's how we convert from spherical to rectangular. To go from rectangular to spherical, we got rho squared equals x squared plus y squared plus z squared. And this should be kind of make sense for us. If I want to find the radius, it's really just a Pythagorean theorem. So that's just our Pythagorean. To get the angle, to get theta, well, let's come back up here. Well, theta, yep, this is my xy plane, right? This point Q has an xy coordinate, so I can get theta by just looking at the inverse tangent of x and y. That's how we get theta. And then to get phi, it's the arc cosine of z over the hypotenuse. Well, let's take a look at where that comes from. To get phi here, I'm looking at this triangle. So this is going to be the adjacent, so it's cosine, inverse cosine, the adjacent z over the hypotenuse, which is our x squared plus y squared plus z squared, right there. So it's just going to be looking at this right triangle right over here. So in other words, this is our, if you want to think about it as z over rho, right there. That's z over rho. It's the adjacent over the hypotenuse. And we're going to take a look at some examples there in just a few moments. Now, where the cylindrical coordinates are good at representing surfaces that are cylindrical in shape, in other words, almost circular in shape, the spherical system is used for surfaces that have point or center symmetry. For example, spheres, ellipses, cones, and the like. So we're going to take a look at a bunch of examples here in just a few moments on how to convert them. So let's go ahead and take a look at the next example, some examples on how to convert these. So we want to convert the following point into a spherical coordinate. So let's go ahead and do that. If I want to convert this to a spherical coordinate, there's my x, there's my y, there's my z. To get rho, remember we need rho first. Rho is just the square root of all of these squared right here. So that's going to become 4 plus root 2 squared is 2 plus 16 times 2, which is 32. So rho is just going to be the square root of, what's that, 38. To get theta, my rule said it's going to be the inverse tangent of y over x, so the square root of 2 over 2. And we should know that theta is going to be 0.615 radians if you use a calculator, or 35.2 degrees if you're going to use degrees. Either one's fine. Phi, get it? Phi. To get phi, it is going to be the arc cosine. Remember this, it's just going to be z over phi. That's the best way to remember it. So phi is going to be the arc cosine of 4 root 2. There's my z over rho, which we already have. There's my z over the square root of 38. And if you just type that in your calculator, I got my calculator here. I am in radians, so you can use this in degree mode if you want. So since I'm already in radian, I might as well use that. I am going to go inverse cosine, arc cosine, 4, whoops, let me do this. I don't know, there's a 9 there, sorry about that. Arc cosine 4 root, there we go. I think I'm ready now. I should type it like this because it makes it as a fraction, makes it a little bit easier for us. 4 root 2 over the square root of 38. And I'm going to type that as a decimal, and I'm going to get 0.409. So what we're going to wind up with is root 38. There's my rho. Theta. I'm going to keep it in radians, 0.615 radians and 0.409 radians. But if you put in degrees as well, that's fine. There's theta and there's phi. Very easy to do. Very easy. Converting to from spherical to rectangular, oh, it's a little bit nastier. There's my rho, there's theta, and there's phi. So we know x is going to be our rule. If we turn over the page, x is going to be rho sine phi cosine theta. So rho sine phi cosine theta. So we're going to get rho, which is 9, the sine of pi over 3, the cosine of pi over 4, and let's see, we should be able to do this one pretty easily. This is what, 9, the sine of pi over 3 is root 2 over 2, and that's, oh no, I always messed it up. It should be the sine of pi over 4 and the cosine of pi over 3. Have my answer right. Come look at my answer key. And this is cosine of pi over 3 is 1/2. There we go. I think I got that sine because phi was pi over 4. Be very careful. Don't mess up like I did. So we get 9 root 2 over 4. Let me write that down again. 9 root 2 over 4. There's our x. To get y is, again, if we look at our rule, it is rho sine phi sine theta. Rho sine phi sine theta. I won't mess this one up. Y equals rho. The sine of rho is pi, sine of phi is pi over 4, and then the sine of theta, which is pi over 3. So we would get 9 times root 2 over 2 times, and the sine of pi over 3 is root 3 over 2, and we would get 9 root 6 over 4. And there's a y value. To get z, again, this is not the easiest to do. It's easy to make mistakes, as you can see what I just did there. And z, we are going to say that is rho cosine of phi. So this is rho cosine of phi. So we get rho, which is 9 times the cosine of pi over 4. So that's going to give us 9 times root 2 over 2. So as a point, we would get 9 root 2 over 4, 9 root 6 over 4, 9 root 2 over 2. And that would be the coordinates for our point. Now, one thing I really like about this is sometimes just how much easier it is to do rectangular coordinates, in spherical coordinates. Let's just look at this point right here. Okay? X, Y, Z. What this is telling me is I'm going to rotate pi over 3 down here. Rotate the pi over 3 right there. And then I am going to measure, so I have a point right here, and that's going to go straight up. And I'm going to measure along the z-axis. And I can draw a little line right there. And this angle right here is pi over 4 radians. And there's our radius right there. And we only go out 9 units. And that would be our point. It's very nice to do. You measure on the xy plane, draw your radius, and then just measure it along the z-axis. Get your radius right there. So there's our point. When you go to part 2, we're going to take a look at how we can convert using equations. I'll see you then. Bye.